Solving large imperfect information games. Using CFR+. Oskari Tamerlin. OT@ikai.fi. July 21, 2014. Abstract. Counterfactual regret minimization and variance, e.g. public chance. Sampling CFR and pure CFR have been known as the best approaches for creating approximate Nash equilibrium solutions for imperfect in 4-mat-ion games such as poker. This paper introduces CFR+, a new algorithm that typically outperforms the previously known algorithms by an order of magnitude or more in terms of computation time, while also potentially requiring less memory. 1. Introduction. Counterfactual regret minimization, CFR, is a technique for solving extensive form games with imperfect information. CFR and its numerous variants are based on regret matching. 2. A self-playing game theoretic technique that chooses strategies proportional to positive cumulative regrets. In this technical report, we introduce a new CFR-like algorithm that instead uses a new variant of regret matching that is empirically shown to perform better by an order magnitude or more. 2. Algorithm. The most straightforward CFR variant is often called a vanilla CFR, or just CFR. In this variant, the entire tree is traversed at each iteration and no sampling is performed. There are 4 common ways vanilla CFR can be implemented in: simultaneous updates scalar form, alternating updates scalar form; simultaneous updates vector form, alternating updates vector form. With simultaneous updates, each iteration has a single pass where both players' regrets and strategies are updated. In alternating updating, there are 2 passes, in which one player is updated in each pass. The difference between scalar and vector forms can be found in E3. CFR+ is a vector form, alternatingly updating algorithm. CFR+ substitutes the regret matching algorithm used in CFR with a new algorithm, regret matching plus, using the definition of counterfactual value 6 sigma, i.e. in E3, define the cumulative counterfactual regret plus at information set I for actioner up to time t as r plus t underscore I a equals max 6 t underscore I 6 t I 0 for t equals 1 and max r plus t1 underscore I a plus 6 t underscore I 6 t I 0 for t greater than 1. The new strategy is produced by t plus 1 equals r plus t underscore I sum in r plus t underscore I if the denominator is positive and once I otherwise. Unlike in CFR, with CFR plus the current strategy profile empirically either most converges or converges to an approximate Nash equilibrium directly, so no averaging step is necessary. However, using weighted averaging, the straight geese can be further optimized to converge faster. The weight sequence used in CFR plus is simply weight equals max TD 0, where D is the averaging delay in number of iterations. The implementation is described in more detail in Algorithm 1. C3-4. The meaning of the symbols used. 3. Compressibility. Another advantage of CFR plus is that many of the cumulative regret values are 0, whereas in CFR, negative regret continues to accumulate indefinitely. This reduces the entropy of the data needed during the computation. Using techniques such as fixed-point arithmetic, instead of floating-point arithmetic, linear and non-linear prediction, context modeling, and arithmetic coding, or asymmetric numeral systems, high compression ratios can be attained in large poker games. Details of CFR plus and compression are outside the scope of this paper and will be discussed in a future publication. For results, We compare CFR Plus to the fastest CFR variant seen during our tests in one card. Poker, the vector form vanilla CFR with alternating regret updates, the same form CFR Plus uses. We observe that 1. CFR Plus current strategy seems to converge slowly when the deck size is small, and 2. CFR Plus average strategy converges more than an order of magnitude faster than CFR. Again, we see a similar difference in performance. 5. Conclusion. In this technical report, we briefly introduced CFR Plus, compared it to CFR, showing more than an order of magnitude improvement in converge time. In a future paper, we will attempt to explain the mathematics behind the algorithm in more detail. Acknowledgements. Thanks to Ronan Osile and Michael Bowling for their help and advice.